In this section, we'll discuss about the coefficient of determination. What is the meaning of this coefficient of determination? The coefficient of determination is used for measuring the goodness of fit of the data. Goodness of fit of the data. The coefficient of determination explains the goodness of fit of the regression line to given data or to the given sample. If the estimated beta 2 cap lies on a straight line, then we will say that it's perfect fit. There is no deviation. Everything is on the perfect. Everything is on the straight line. That is, if the estimated value is on the straight line and there is no observations here and there, then we will say that it is a perfect fit. If it is on the straight line, we will say it is a perfect fit, but it is very rare case. There will be some errors in the model, some outliers will be there, some positive error terms will be there, some negative terms will be there. Therefore, the estimated value won't be on a straight line. There will be some deviations in the fitted line. The coefficient of determination is defined as r square. This small r square. The small r square is used in the case of two variable model, and capital R square. This is used in the case of multiple regression model. If the number of variables, independent variables, are more than one, we will use the capital R square or the multiple R square. Or the coefficient of determination R square. This coefficient of determination R square is a summary. That is, in the case of this two variable case, it is denoted by small r, and in the case of multiple regression model, it will be denoted as capital R square. And it is a summary measure that tells us how well the sample regression line fits the data. How well the sample regression line fits to the data are given through this coefficient of determination. And this can be explained by the following figure. Here, the explanation of y on x's are given in different different Venn diagrams. Here, y and x are independent. There are no relationship. In this case, we will say that the coefficient of determination is 0. Here, some part of y are explained by x, but there exists some correlation between these two variables. Here, the correlation is very high, or in this case, the x explains more. The explanation of independent variable, or the dependence of the independent variable on the dependence of the y on x, is more than this one, or it explains more than 50%. Here, y completely depends on the x, so there is a perfect fit. Then in this case, the coefficient of determination will be equal to 1. Here, if there is no relationship, it will be 0. In accordance with that, the dependency, the value will be different. Here, therefore, it lies between 0 to 1. If there is no the y and x are independent, r square equal to 0. Then r square increases as the dependency increases. If y is completely explained by x, then the r square equal to 0. That is, it ranges between 0 to 1. This is the first point. Then another points to remember: in the case of two variable model, it is denoted as small r square. Multiple regression model, it is denoted as capital R square. And what is this goodness of fit, measure of goodness of fit, or R square, or coefficient of determination shows? It shows how well the sample regression line fits the data, or to which extent the dependent variable is explained by the independent variable, is explained by the coefficient of determination. This can be proved as follows. Further, let us consider the equation yi equal to yi cap plus ui cap. Then let us consider We know that yi equal to yi cap plus ui cap. This deviation from this can be written as small, this is small yi equal to yi cap plus ui cap. This in deviation form, this can be written as. Then square this term. Then square this term means yi square equal to yi cap square plus ui cap square. Then take this sum. Then it will be equal to sigma yi square equal to sigma yi cap square plus sigma ui cap square. Or this can be square both term, that is yi cap square. Now square both the term, yi square equal to yi cap plus ui cap square. Then take this sum, that is summation of yi square equal to summation of sigma yi cap plus ui cap the whole square. Then yi cap plus ui cap the whole square can be written as yi cap plus ui cap square can be written as yi cap square plus ui cap square plus 2 yi cap ui cap. Then substitute the then distribute the sigma. Then it will be equal to sigma yi square plus sigma yi cap square plus sigma ui cap square plus 2 sigma yi cap ui cap. Then this will be equal to sigma yi square equal to sigma yi cap square plus sigma ui cap. Since yi cap ui cap equal to 0, this term will be 0. And we can also make use of another property, namely yi cap equal to beta 2 cap xi. Then we can substitute yi cap square equal to beta 2 cap square, this is square beta 2 cap square sigma xi square. This is yi cap is beta 2 cap xi. Since this is square, this can be written as sigma beta 2 cap sigma or beta 2 cap square sigma xi square plus sigma ui square. Or simply we can say sigma yi square equal to sigma yi cap square plus sigma ui cap square. And this equation can be written as follows, that is first term is sigma yi square. This sigma yi square is known as total sum of square. Sigma yi square equal to sigma of yi minus y bar the whole square. Yi minus y bar is small yi. Here square is sigma yi minus y bar the whole square. That is the sigma yi square. This is total variation of actual yi from its mean value or about their sample mean. This is termed as the total sum of square. Second term is sigma yi square. Sigma yi square is sigma of yi cap minus y bar the whole square. That is beta 2 cap sigma xi square. This is termed as explained sum of squares. The first one is total sum of square. This shows the deviation of actual from its mean value. This shows the deviation of the estimated value from its mean value. Therefore, this is explained sum of squares, or it is due to the regression. That is, ESS is variation of the estimated yi, that is yi cap, from its mean value, that is yi cap bar equal to yi, which appropriately may be called the sum of squares due to the regression. Or that is due to the explanatory variable, or explained by the regression, or explained by the sum of squares. And the third term is sigma ui cap square. This is the residual sum of squares. The residual or unexplained variation of y value above the regression line, or the residual sum of square. This is the RSS. Therefore, the three terms are, the first one is sigma yi square. That is sigma of yi minus y bar the whole square. Second one is sigma yi cap square. This is the estimated value, the yi cap square minus y bar. This is the second term. And the third one is the ui cap square. This is termed as residual sum of squares. Therefore, the above equation can be written as sigma yi square equal to sigma yi cap square plus sigma ui cap square can be written as TSS equal to ESS plus RSS. That is, total variation in the observed y values about their mean value can be partitioned into two parts, one attributable to the regression line and the other to the random forces or the error term. And this is explained by this diagram. Here the total variation is given here. This y mean value is here y bar, and the total variation, total explanation, total sum of square is given by here, that is yi minus y bar. This is the total variation, and this total variation can be divided into two portions. This one up to this point, this is the regression line, this is due to regression, and here this is the outlier, this is due to the error term or due to the residual. That is, total sum of squares is equal to, it is equal to the explained sum of squares or to the sum of squares due to the regression plus sum of squares due to the residuals. This is the meaning of the earlier explanation. That is, sigma yi square equal to sigma yi cap square plus sigma ui cap square. TSS equal, this is TSS, this is ESS, and this portion is the RSS. This is the fitted line, and here is the observation or the UI cap square, and therefore this portion is the UI cap square. From this we can explain the coefficient of, from this relationship we can explain the coefficient of determination. That is, TSS equal to ESS plus RSS. Now divide the whole equation by TSS. That is, TSS by TSS equal to ESS by TSS plus RSS by TSS. Then TSS by TSS equal to 1, ESS by TSS plus RSS by TSS. What is this ESS by ESS? ESS is sigma of yi cap minus y bar the whole square, and TSS is sigma of yi minus y bar the whole square. RSS is sigma ui cap square divided by sigma yi minus y bar the whole square. Now the R square is defined as ESS by TSS. This component is termed as R square, or sigma yi cap minus y bar the whole square divided by sigma of yi minus y bar whole square is the RSS, is the R square. Or we can write from this R square equal to, from this 1 equal to R square plus sigma ui cap square divided by, here 1 equal to R square plus sigma ui cap square by sigma of 1 equal to R square plus sigma ui cap square divided by sigma yi minus y bar whole square. Then if we take R square here, then we'll get 1 minus this one, 1 minus sigma ui cap square by 1 minus y bar equal to y bar the whole square equal to the R square. If we take this term to here, then if we take this term to here, we'll get 1 minus sigma ui cap square equal to R square. This is given here, R square equal to 1 minus sigma ui cap square by sigma of y minus y bar. This is nothing but RSS by TSS. That is, 1 minus RSS by TSS will give the R square value. That is, R square equal to ESS by TSS, or sigma yi cap square by sigma yi square. That is, yi cap square is sigma of yi cap minus y bar is denoted as sigma of yi cap square, and sigma of yi square is sigma of yi minus y bar the whole square is denoted. Then sigma yi cap square is beta 2 cap square sigma xi square by sigma xi square, or beta 2 cap into sigma xi square by sigma yi square. Is defined as the sample coefficient of determination and is the most commonly used measure of goodness of fit of the regression line, and it measures the It measures the proportion of percentage of total variation in y explained by the regression model. This is the meaning of R square. That is the proportion of total variation in y explained by the regression model. That is ESS by TSS. Two important properties of R square are: it is a non-negative quantity. Second one, it lies between 0 to 1. 0 means no correlation, means there is no relationship between the regressant and the regressor. Beta 2, if beta 2 equal to 0, then R square equal to 0. If it equal to 1, there is a perfect fit. These are the two important properties. It is a non-negative quantity and equal to 0. If there is no relationship between the regressant and the regressor, then the R square will be 0. Then that equal to beta 2 equal to 0. This can be explained as follows. If R equal to plus 1, perfect fit, then perfect positive correlation, perfect positive relationship, then the curve will be like this. If there is perfect negative correlation, there is perfect negative relationship, this will be a downward one. And then if it is close to plus 1, this will be like this. Close to negative minus 1, this will be like this. X positive but close to 0 can be shown like this. X negative, this is an upward. X negative but close to 0 is like this. If R equal to 0 can be shown this. If Y equal to X square, then R equal to, here the coefficient of correlation is given. Coefficient of correlation measures the degree of association, and this is the square root of R square is the coefficient of correlation R. And the properties of coefficient of correlation are, it can be positive or negative. It lies between -1 to +1. That is -1 to +1. R lies between -1 to +1, but R square lies between 0 to 1. That is an important point to remember. 0 when two variables, when independent and the dependent variables are entirely independent, then 0. If there is perfect fit, then it is 1. But coefficient of correlation lies between -1 to +1. It is symmetrical in nature. That is the coefficient of correlation between x and y is Rxy equal to the Ryx. It is independent of origin and scale. These are some of the important properties. Here we explained the coefficient of determination. Coefficient of determination shows how well the fitted regression line explains the sample data. For that, we use the coefficient of determination R square. In the case of the simple regression model or two variable regression model, it is denoted as small r square, and in the case of the multiple regression model, it is denoted by capital R square. It lies between 0 to 1, and it is defined as ESS by TSS. From that, we can derive so many other relationships also. This explains the goodness of fit of the data.